And this is the moment that you've all been waiting for. So we've been building up to coming to the formal expression of Gauss's law. And by the way, this is my series on university physics, roughly following Young and Freedman's university physics textbook. And so there are four key equations in electromagnetic theory. We've seen one of them in chapter 21, Coulomb's law. And the end of chapter 21 had some pretty complicated computations with regard to how strong the electric field was and so forth. Gauss's law simplifies all that. And even though it has Gauss's name on it, it was really, this was systematized by James Clerk Maxwell in the mid to late 1800s. Let's get into it. So we've seen in previous sections a kind of qualitative statement of Gauss's law. Remember this? The net electric flux through a closed surface is directly proportional to the net charge inside that surface. Pretty disarming. But this, Coulomb's law, you had to add up the charges. What's the distance? It's complicated math sometimes. Gauss simplified all of that by this idea of an imaginary container. Doesn't matter what the shape of the container is, but imaginary container in which a charge was enclosed. And so basically what he found is that if you want to know how much electric flux is coming out or going in, frankly, if it's negative, if it's positive, it's going out, if it's negative, it's going in, how much electric flux is coming in and out of this imaginary box, it's directly proportional to the amount of charge that's inside whatever that surface, whatever that box or sphere or cube or whatever it is. It's proportional to it. And so all we need, when something's proportional, all we need is a constant to make it an equation. So the consequences of this approach is that if charges are outside of a box, they're not going in or out of the box, they're outside of it, there's zero net flux related to that space from that charges. It's only the enclosed charge, the net charge inside the surface. Same thing. If a flux comes in and goes out, it cancels out. You've got the negative coming in and the positive going out, and they cancel out because they're equal. And so a flux coming in and out, zero net flux. It's the enclosed charge within a surface that tells you what the electric flux is coming out or going into that surface. So another thing we've discovered, and Young and Freedman go to great lengths to show this, is that it doesn't matter what the shape or size of the surface is. I've said this. It doesn't matter whether it's a square, a cube, or a sphere. It's very spatial. The spatial dimensions cancel out. Doesn't matter. Spatial factors cancel out. And so what it basically leaves us with is that the total electric flux coming in, going out of a surface is equal to the enclosed charge divided by this constant that's sometimes called the Q is the enclosed charge, and then the Epsilon Zero is sometimes called the constant of permittivity, of free space, or something like that. We encountered this constant in chapter 21. Basically, this constant is like 1 over 4 pi. There's a constant in Coulomb's law. It was called K initially, and basically we use that constant K in Coulomb's law to get it from proportional to an equation, right? Whenever you want to move something from a relationship that's proportionate, if you want to move it to an exact equation, you find what the constant of proportionality is. Well, with Coulomb's law, initially that constant was K, and what physicists have found is that if we express that K in terms of 1 over 4 pi epsilon 0, a lot of things work out. I don't know why. I don't explain. I'm trying to tell myself ours is not to question why. Ours is just to trust the physicists or die. So epsilon 0 is this constant that appears often in these electromagnetic equations, and it is basically a way of taking the constant in Coulomb's law and putting it in the form of 1 over 4 pi epsilon 0. You just do a little math, and that's what it is. If you want to know what it is, its number, the epsilon sabot, or epsilon 0, is 8.854 times 10 to the minus 12th power, Coulomb squared over Newton meters squared. It's a constant. And that constant makes it an equation. It takes the proportionality between the electric flux and the enclosed charge and makes it an equation. Okay? Don't need to understand it to use the math. You can use this equation whether you understand what epsilon sabot is or not. Okay, so now let's bring in some calculus. Let me pause it so I can make it more of a suspenseful thing. Okay, there, now we can have a drum roll. So if we bring in calculus, here's what it ends up looking like. You'll see that we're still looking at the total flux, the flux, electric flux that's coming out of any surface. And we've got this at the other end, same thing. The total includes, we've got to put a capital Q because it's the total enclosed charge. And ENCL means enclosed, right? That's simple enough. And there's epsilon sabot again at the end there. So we've got the same thing we just had on the previous page. By the way, the next video is going to do some applications of this, so we'll get to see a little bit more of what it actually means. But here's how we might express it. And again, if you look at the previous videos in this chapter, no surprises here. It is the surface integral, okay? That little circle there, we've not seen that before. The surface integral, that means the sum of all the little areas on the surface of something. Doesn't matter what shape, but if you were to take the sum of all the little, and then dA means the infinitesimal little area bits. If you were to add them all up, and if you were to add up the electric field coming out perpendicular, the dot means it's perpendicular. Another way I've seen this expressed is with that N arrow, the normal vector. It's a unit vector of 1 perpendicular. It basically says it's got to be perpendicular. The dot means it's got to be perpendicular. So all the little electric fields coming out perpendicular. If you add up all of those little electric fields on the entirety of the surface of whatever imaginary sphere, box, cube, cone, whatever, if you add up all the infinitesimal little areas, and the component of the electric field coming out of it on the surface, that's what the circle means there, it would equal the total enclosed charge divided by the constant of permittivity. And so, again, no surprises here. This is exactly what we've seen in the previous videos. Other ways of expressing it, this dot product is the cosine of phi. That's the angle between the perpendicular and whatever angle it's coming out at. This is from, look at the previous video, and it goes over all of that. So electric field cosine phi dA is the same thing as E dot dA. And we can also say that the electric field, this upside down T means perpendicular. The electric field perpendicular to the surface for each infinitesimal dA. I don't think we really need to know a lot about that middle bit right now, because it's this end bit that we're going to actually use. What is the enclosed charge divided by a constant that I told you was 8.8 blah times 10 to the minus 12 on the previous chart? I think it's going to be pretty easy. James Clerk Maxwell made it very easy drawing on the precedence of Gauss. And there you have it. That is Gauss's law, the second main equation of electromagnetivity that we've seen so far.